Hi, last time we introduced a rumor spreading model and calculated the mean time for a rumor to spread on the complete graph on n vertices. And we saw that the mean rumor spreading time scaled logarithmically in the number of nodes, so it was approximately 2 times log n. This time we are going to look at more refined we are going to try and describe the random variable of the rumor spreading time and prove a limit theorem for this random variable. So I'm hopefully sharing screen now. So we calculated the mean rumor spreading time ETN and showed that it scales as 2 log n. And this time we are going to look at fluctuations around this. For today's lecture, we are going to need to know about some probability inequalities. So I'll start by introducing the ones we are going to need. The most elementary inequality is probably what's known as Markov's inequality. So it says that if x is any non-negative random variable and it has finite mean, then the probability that it exceeds some number c is bounded in this way in terms of the mean and c. I'm not going to give a formal proof of this. You can find it in various references, but let's just look at the intuition behind it. There are 75 people on this course. Let's say that the mean number of hours a week that each of us spends on social media is 8 hours. Okay, and I want to know how many of us spend more than 20 hours a week on social media. Can you give a bound on this number? So let me repeat the input. There are 75 people. Mean weekly hours on social media is 8. And I want to know how many exceed 20 hours. Okay, so you could, how do you calculate this? So the total time spent by everyone on social media is 75 times 8 hours, which is 600 hours a week. And nobody can spend a negative amount of time. So with 600 hours, the number spending more than 20 hours a week can be at most 30, or has to be strictly smaller than 30. Okay, so that's the bound, and that's exactly what this bound says. And this is called Markov's inequality. The contribution to the mean from x bigger than c from each such x is at least c, so c times that probability can't exceed the mean is what this is saying. So what's the point of a probability inequality like this? So it gives you a way of bounding the probability of events without knowing too much about the random variable. If I gave you the distribution of x, you could calculate this probability exactly. But if we don't know the distribution, or if the distribution is very difficult to calculate exactly, just by knowing the mean, we gain some information. It may not be a very good bound, but it is a bound. And so, it gives us some information. That's the point. So here is a somewhat more refined bound. And this needs knowing a bit more about the random variable. For this, we need to know not only the mean, but also the variance. And in this case, we don't need the random variable to be non-negative. For Markov's inequality, we assumed it's non-negative. Here, we don't assume that, but we have a bit more information. And then the bound says that the probability that this random variable x deviates from its mean by more than c is bounded above by the variance over c squared. Why is this true? The proof of this follows easily from Markov's inequality. So we just apply Markov's inequality to this random variable, x minus its mean squared. This is a non-negative random variable, so you can apply Markov's inequality to it. Its expectation is precisely the variance of x, and this event we are interested in here is the same as the event that x minus cx whole squared is bigger than c squared, and so Markov's inequality gives you this. Okay, and that's the inequality we are going to need for our analysis of the Rumour spreading time. There are other inequalities you can prove if you know a bit more about the random variable. So if you know its moment generating function, for instance, then you can prove tighter bounds known as Chernoff or Bernstein bounds, but we won't go into this. You can again look this up in the notes. And these bounds, you get these bounds by applying Markov's inequality to the random variable e to the theta x, which is always non-negative, even if x isn't. Okay, so Chebyshev's inequality is the main thing we are going to need. Let's now, we calculated the mean of the Rumour spreading time last time, and now we are going to try and calculate its variance. And for that, I need to remind you that the variance of an exponential random variable with parameter lambda is 1 over lambda squared. And we showed that the random variable tk plus 1 minus tk is exponential with parameter n over k times it's exponential with parameter k times n minus k over n. So lambda is k times n minus k over n. 1 over lambda is this quantity here, and so the variance is 1 over lambda squared. That's what we have. And then we write Tn as a telescoping sum. When we wanted to calculate the expectation of Tn, we used linearity of expectation. And for that, we didn't need the fact that these random variables, these increment times until one more node learns the Rumour, these are we didn't need their independence, but now we are going to need it. So let me state my claim here. So I'm claiming that the time from k nodes to k knowing the Rumour to k plus 1 nodes knowing the Rumour, these increment times for different values of k are mutually independent. And this is basically an easy consequence of the memoryless property of the Poisson distribution. So irrespective of what happens between tk and tk plus 1, at time tk plus 1, there are k plus 1 nodes knowing the Rumour. What happens in future depends on the Poisson processes describing when these k plus 1 nodes are going to talk to other nodes, and that's independent of everything in the past. So tk plus 2 minus tk plus 1 is independent of this, etc. So for distinct k, these are all mutually independent. Okay, and now we are going to use the fact that if you have a sum of independent random variables, then the variance of the sum is the sum of the variances. You only need pairwise independence, not full mutual independence, but anyway, we have that. So let me remind you again, the variance of the sum is the sum of the variances for independent random variables. So writing Tn as the telescoping sum, the variance of Tn is the sum of the variances of Tk plus 1 minus Tk. So you get this. Now I've expanded the square here, so I get 1 over k squared, 1 over n minus k squared, and 2 times this product, 1 over k times 1 over n minus k. I've skipped the step where I expand that product in partial fractions. So if you do that, you get this. So all the steps in the calculations are in the lecture notes. I'm not going to go over them in painstaking detail here. But anyway, so you get this as the variance of Tn. You get these 3 terms in the sum. The third term is small. As we saw earlier, the sum of 1 over k is log n. This is also a log n. So you get a log n over n term here, and that's vanishing as n goes to infinity. So this third term is negligible. Okay. The first term here, sum of 1 over k squared, you may not, okay, it's just a fact that this sum is pi squared over 6, or rather it tends to pi squared over 6 as n tends to infinity, so does the other one. And these two things together add up to pi squared over 3. I don't necessarily expect you to know that, but the main thing I want you to note is that this sum is finite. This sum, as n tends to infinity, this sum stays bounded. The sum of 1 over k grew slowly with n. It grew as log n, but this sum is not growing. It's bounded uniformly in n. And you can check that, for example, by comparing the sum with an integral. The integral of 1 over x squared from 1 to infinity is finite. And so this sum is finite uniformly in n as well. That's something you should know. The particular value may not be well known. It just so happens it's pi squared over 6, and these add up to pi squared over 3. Again, a reminder of the big O notation. We have seen this before, so I won't go over it. But the main takeaway from this calculation is that the variance of Tn remains bounded as n tends to infinity, and it is bounded by this constant pi squared over 3. So what have we shown? We've shown that as n goes to infinity, the mean of Tn scales like 2 log n. So if you divide Tn by 2 log n, the mean tends to 1. The variance of Tn is bounded, it's some constant. So if you divide by 2 log n, the variance gets divided by the square of this. So a constant over log squared n goes to 0 as n goes to infinity. Okay, and so I want to put these two things together. We have a sequence of random variables. So let's look at the sequence of random variables, Tn over 2 log n. Tn is what we are interested in, but we have rescaled it. So these scaled random variables converge in mean to 1, and their variance is vanishing. So intuitively, what do you expect? The centering of these random variables is tending to 1. The spread around the centering is getting narrower and narrower. That's what the variance going to 0 says. So they are concentrating close to 1. So intuitively, you expect that these random variables converge in some sense to this constant 1. And that is true in the following sense. So using Chebyshev's inequality, if we look at the deviation of the scaled random variable Tn over 2 log n from 1, we can split this. We can write this difference as Tn over 2 log n minus its mean plus the mean minus 1. The mean is tending to 1, so the mean minus 1 is going to 0. So it's smaller than epsilon over 2 for all n large enough. So this event is a subset of the event that this random variable Tn over 2 log n deviates from its mean by at least epsilon over 2. Okay, and then the mean deviates from 1 by an additional epsilon over 2. Both those things have to happen for this deviation to be bigger than epsilon. And for this probability, we can use Chebyshev's inequality. The probability that this random variable deviates from its mean by at least this much is its variance divided by the square of this, epsilon squared over 4. But the variance tends to 0, so the right-hand side tends to 0. Okay. Okay, so what have we shown here? We've shown that if I fix a positive epsilon, however small I like, say 0.001, then the probability that the rescaled random variable Tn over 2 log n, that it deviates from 1 by more than epsilon, this probability tends to 0 as n tends to infinity. And that's exactly what it means to say that these random variables, the sequence of random variables converges to 1 in probability. So let me remind you of that. We say that a sequence of random variables xn converges in probability to a constant c if the following is true. If for any epsilon positive, the probability that xn deviates from c by more than epsilon tends to 0. So we have shown that Tn over 2 log n converges in probability to 1. That's the second main result about Rumour spreading on the complete graph. The first result said that the expectation of Tn converges to 2 log n, or the expectation of Tn divided by this converges to 1. And the stronger result is that the random variables themselves converge in probability to 1. Okay, so the additional things you should remember from this part is the definition of convergence and probability and the two elementary probability inequalities, Markov's inequality and Chebyshev's, and how to apply these. Okay, the next point I want to make is to connect this Rumour spreading model we studied to another model known as first passage percolation. So let me define the problem. So again, Kn is the complete graph on n nodes. Now let's take it to be undirected. Now, now I take this graph and I put weights on the edges. So on each edge, I put a random weight with an exponential distribution with parameter 1. So think of the length or weight of an edge to be this random variable, which I'll denote W for weight, and I'm labeling the edge UV. The question we want to ask is, we want to fix a single node U and ask what's the shortest path from U to some other vertex V. And we'll denote by DUV the length of the shortest such path. Okay, so it may be just the direct edge. So the shortest path doesn't necessarily have to consist of the single edge, right? By shortest, I mean the minimum weight path. So there's an edge between U and V with length WUV. But maybe the smallest weight path is to go from U to W and then W to V. If these two weights add up to less than WUV, then that's a shorter path. Or maybe you want to go through 10 intermediate nodes. We don't know how many intermediate nodes you want to go through. But the shortest path, meaning the minimum weight path, is obtained by minimizing over all possible paths that go from U to V, the sum of the edge weights along that path. Okay, so that's the definition of the shortest path from U to V. What we are going to be interested in is the random variable, which looks at all these minimum weight paths and looks at the one to the furthest away vertex. So there's some, so to each vertex V, there's some distance from DUV is indeed the distance from U to V in this sense, where the weights denote the edge lengths. And du is the diameter, is the radius as seen from U. It's the distance to the furthest away vertex. And we can ask either about the random variables duv or about this random variable d sub u. And my claim is that the random variable d sub u is essentially the same as the random variable t sub n, the Rumour spreading time, up to a rescaling. So if I had given the edges independent weights, which are exponential with parameter 1 over n rather than exponential with parameter 1, these two would have been the same. But because I've put x1, you have to rescale them, and then these two are the same. Okay, I'm not going to prove this claim. You should think about it. And in fact, you're asked to show this in one of your homework problems. I just wanted to say that that the Rumour spreading problem is also related to this problem of shortest paths on random edge weighted graphs. And this is also called first passage percolation. So if you're thinking of some liquid starting at U and percolating out through the graph, and WUV denotes the length of time it takes for it to spread from U to V along the direct edge, then these times DUV tell you when the liquid has first reached the vertex V, and this tells you when the liquid has reached all the vertices, and that's the terminology why it's called percolation. First passage is where you're minimizing the sum of the weights. You're looking at the shortest path. If you replace this by the max, it's called last passage percolation. That's the longest weight path, the longest path from U to V, excluding cycles. Okay, that's just a related optimization problem on graphs. Some remarks. So the main takeaway message I'd like you to take from this analysis is that Rumour spread quickly and the spreading time scales only logarithmically in the population size. I mentioned that that it's much more natural maybe to think of the discrete time version of this model. That's also been studied, and the spreading time is also logarithmic. It scales like log n, but instead of the constant 2 in front, it's a different constant, a slightly larger constant. Okay, I said the reason I introduced the model I did is that it's very easy to analyze. And it's easy because of the memoryless property of the exponential distribution. So we only had to keep track of the times tk when k nodes first learned the Rumour. We didn't need to know anything about what happened before then and how much longer it takes until one more node learns the Rumour. Also, at a time, because time is continuous, only one node learns the Rumour at any time. What makes the discrete time version complicated is that in each time step, a random number of nodes learn the Rumour. It doesn't increase by one at a time, but there are jumps of all possible sizes, and that makes this model more complicated to analyze. Okay, but the continuous time model is much simpler. But even though we use the memoryless property, in fact, the results are fairly insensitive to this assumption. You can show by starting with this analysis that the results carry through to a large class of other models, not all other models, but a large class. So they hold for any edge weight distribution which has density 1 at the origin. An example of this is the uniform. Okay, it's easier to talk of edge weights in the first passage percolation version of the problem rather than to Rumour spreading times, but you can restate it in terms of that as well. So instead of having x1 edge weights, if you had uniform 0, 1, uniform edge weights between 0 and 1, they have same density 1 at the origin, and so you can argue that the shortest path distribution in the large n limit is also the same, or the mean of it certainly is the same. And the reason for this is that when you look from any vertex, there are n possible edges from this vertex. There's a very large number of them. And it's only the smallest few of these that matter, the smallest log n of these that matter. So the smallest weight edges will have weights very close to 0, and it's only the density near 0 that matters. Okay, maybe it's not so, you've just seen this model, it might not be so easy to see this, but if you spend some time thinking about it, you can convince yourself of this fact. So by analyzing this model with exponential edge weights, you then realize that you can say something about models in a whole class of other edge weight distributions. Okay, so that's all I wanted to say about Rumour spreading on the complete graph, for which we were able to say a lot. We could calculate the expected time for Rumour spread exactly. We were also able to get the variance also pretty much exactly and use this to prove convergence and probability in the large n limit. Next, we are going to move on to looking at Rumour spreading on general graphs. And in this case, we'll be able to say much less. We'll only be able to get bounds rather than exact expressions. But these bounds will work for a wide range of graphs. But we'll start on that next time, and I'm going to stop here with the Rumour spreading model on the complete graph.